Picture a realm beyond our three dimensions, a place where the rules of reality break down completely. For Victorian scientists, the fourth dimension represented a doorway to the divine, a spiritual plane waiting to be discovered. But for horror writer H.P. Lovecraft, those higher dimensions held only terror, filled with impossible geometries and creatures that defied comprehension. His character Walter Gilman explored these extra-dimensional spaces in his dreams and paid the ultimate price. Now, here's the twist that'll blow your mind. Modern physicists have discovered we don't need more dimensions to explain the universe. We need fewer. Our entire three-dimensional reality, everything you see and touch, might actually be nothing more than a thin two-dimensional hologram. If that sounds impossible, smash that like button and subscribe, because what you're about to discover will change how you see everything. The key to unlocking this cosmic secret was found in the darkest, most destructive objects in existence, black holes. Prepare yourselves. We begin. In the early 1970s, a young physicist named Jacob Bekenstein stood at the edge of a scientific precipice, staring into one of the most profound mysteries the universe had ever presented to humanity. And what he found there would shake the very foundations of physics itself. Bekenstein was a devoutly religious man, someone who saw the exploration of the cosmos as a form of worship, a way to understand the mind of God by unfolding the mathematical secrets hidden in creation. He believed that the more we learned about nature, the closer we came to knowing the divine. Yet the object of his fascination was anything but holy. It was arguably the most demonic force in all of existence. Black holes, regions of space-time, so catastrophically warped by gravity that nothing, not even light itself, could escape their grasp. These weren't just cosmic oddities or theoretical curiosities buried in obscure equations. They were real, tangible monsters lurking throughout the universe, devouring stars, ripping apart planets, and sometimes consuming entire galaxies in their insatiable hunger. There is no greater destructive power in all of creation, no force more final, more absolute in its dominion over matter and energy. When something crosses the event horizon of a black hole, that invisible one-way boundary marking the point of no return, it's gone forever, sealed away from the rest of the universe for all eternity. At least, that's what everyone thought. Black holes had first emerged from the mathematics of Einstein's general theory of relativity, that revolutionary framework describing gravity not as a force pulling objects together, but as the curvature of space-time itself, where massive objects like stars and planets create dips and valleys in the fabric of reality, and other objects roll along those curves like marbles on a stretched sheet. Black holes represented the most extreme version of this curvature, places where the fabric of space-time had been torn and twisted so violently that it created a bottomless pit, a cosmic trapdoor leading to nowhere. The Nobel Prize-winning physicist Subrahmanyan Chandrasekhar had called them the most perfect macroscopic objects in the universe, constructed from nothing but our concepts of space and time themselves. But despite this mathematical perfection, black holes created more headaches for physicists than they solved, particularly when it came to two grand mysteries that seemed fundamentally unsolvable. The first mystery was the singularity, that point of infinite density lurking at the very center of every black hole, where all the matter that had fallen in gets compressed down to a region of literally zero volume, creating densities that shoot off toward infinity. Infinite anything in physics is usually a giant red flag, signaling that something has gone terribly wrong with your equations, that you've pushed your theory beyond its breaking point into territory where it no longer makes sense. General relativity predicted these singularities, but their existence clearly showed that Einstein's beautiful theory was incomplete, that there had to be some deeper, more fundamental framework underneath it all that could explain what was really happening at the heart of a black hole. Unfortunately, those singularities are forever locked away behind the event horizon, that one-way membrane sealing off the black hole's interior from the outside universe. So even if you were brave enough, or foolish enough, to dive past that boundary, to investigate what secrets lay within, you'd never be able to report your findings back to anyone outside. You'd be trapped forever, falling inexorably toward that central point of infinite compression, with no possibility of escape or communication. And it was these event horizons, these mysterious boundaries marking the point of no return, that presented the second great mystery, the one that would ultimately consume Jacob Bekenstein's attention and lead to one of the most revolutionary insights in modern physics. Black holes were the only places in the entire universe where you could enter but never leave, where information and matter could go in, but nothing could ever come back out. And this raised a deeply troubling question that struck at the heart of how physics operates. You see, physics is fundamentally about prediction, about using the current state of a system to calculate what will happen next. And that predictive power depends entirely on information, on knowing the positions, velocities, energies, and quantum states of all the particles involved. In classical physics, if you knew everything about a system at one moment in time, you could, in principle, calculate its entire future and past with perfect accuracy. Quantum mechanics complicated this picture somewhat by introducing fundamental uncertainty and probability into the mix, but the basic principle remained the same. Information was sacred. It could be transformed and scrambled and spread out, but it could never truly be created or destroyed. This principle, known as unitarity, or information conservation, was one of the bedrock foundations of quantum mechanics, a law so fundamental that breaking it would essentially tear down the entire edifice of modern physics. And yet black holes seemed to do exactly that. They appeared to swallow information whole and make it vanish from the universe forever. When a star collapses into a black hole, all the intricate details about that star, its chemical composition, its temperature distribution, its magnetic fields, every quantum state of every particle that made it up, all of that information disappears behind the event horizon, where no one can ever access it again. From the outside, black holes are absurdly simple objects. They present only three quantifiable properties to external observers: their total mass, their electric charge, and their spin or angular momentum. That's it. Just three numbers to describe an object that might contain the crushed remnants of millions of stars. Everything else, every other detail, every bit of complexity, gets hidden away forever behind that impenetrable barrier. Bekenstein would later call this the no-hair theorem, a deliberately provocative phrase suggesting that black holes are utterly bald, completely stripped of all the complex features and details that characterize normal objects in the universe. His mentor John Wheeler loved the phrase and helped popularize it, though the famous physicist Richard Feynman found it obscene and objected to its use. But despite Feynman's complaints, the name stuck in the physics community. Some theorists initially proposed that black holes might be regions of zero entropy, places of perfect order with no information content whatsoever. But Bekenstein immediately realized this couldn't possibly be right, because if it were true, you could exploit black holes to violate the second law of thermodynamics, one of the most ironclad principles in all of physics. The second law states that entropy, that measure of disorder and randomness in a system, never decreases in a closed system. It either stays the same or increases over time. This is why hot coffee cools down, why ice melts in warm rooms, why broken eggs never spontaneously reassemble themselves. Entropy always flows in one direction, from order to disorder, from organization to chaos. But if black holes had zero entropy, you could take a hot gas filled with entropy, with all those randomly moving molecules, carrying disorder, and toss it into a black hole, and poof, that entropy would simply disappear from the universe, vanishing behind the event horizon, and leaving the total entropy of the cosmos lower than before. That would be a blatant violation of the second law, an impossible scenario that would undermine decades of thermodynamic theory. So Bekenstein reasoned that black holes must have entropy. They must contain information. But how much? And where was it stored? This is where Bekenstein made his truly revolutionary leap. In 1972, while still working on his PhD dissertation, under John Wheeler at Princeton, he proposed something that seemed bizarre, almost absurd, that black hole entropy should be proportional to the surface area of the event horizon, not to the volume enclosed within it. In normal thermodynamic systems, entropy scales with volume. A bigger gas chamber contains more molecules, and therefore more entropy than a smaller one. But Bekenstein was claiming that for black holes, it was the two-dimensional surface area that mattered, not the three-dimensional volume. The larger the event horizon, the more surface area it had, the more entropy the black hole contained. This was a radical departure from conventional thinking, suggesting that somehow information was being stored on the surface of the black hole, spread out across that spherical boundary, like data encoded on a hard drive. At the time, this was just a conjecture, an educated guess based on careful reasoning about thermodynamics and information theory. But it was still just a guess, one that many physicists found difficult to accept. And that's where Stephen Hawking entered the picture. Hawking, unlike the religious Bekenstein, was a committed atheist who believed that the laws of physics themselves provided all the explanation we needed for existence, without requiring any divine intervention or personal deity. He would later say that God is just the name people give to the reason we exist, but he thought that reason was simply the laws of physics, not someone you could have a relationship with. Despite their different philosophical outlooks, there's no record of any tension between Hawking and Bekenstein over their religious views. Hawking's objections were purely scientific, focused on what he saw as fundamental problems with Bekenstein's theory. Hawking argued that black holes couldn't possibly have entropy because they didn't radiate, they didn't emit heat or particles. They just sat there absorbing everything that came near them without giving anything back. And if they didn't radiate, they couldn't have a temperature. And if they didn't have a temperature, they couldn't have entropy, because entropy and temperature are intimately connected through the laws of thermodynamics. So in Hawking's view, Bekenstein's entire framework was built on a flawed foundation, mixing concepts from thermodynamics with objects that didn't actually behave thermodynamically. Determined to prove his rival wrong, Hawking set out to carefully analyze the quantum mechanical behavior of fields near a black hole's event horizon, following the mathematics wherever it led, expecting it to demolish Bekenstein's theory once and for all. But as he worked through the intricate calculations, something shocking emerged from the equations, something that would forever change our understanding of these cosmic monsters and earn Hawking his place in the pantheon of physics legends. In 1974, after months of painstaking work, Hawking published a paper that sent shockwaves through the physics community. He had discovered that black holes do radiate, they emit particles, they glow with a faint thermal radiation, now known as Hawking radiation, and they have a precise temperature that depends on their mass, with smaller black holes burning hotter than larger ones. Bekenstein had been right all along. Black holes did have entropy. They did behave like thermodynamic objects, and Hawking's calculation even provided the exact mathematical relationship between the event horizon area and the entropy, confirming and refining Bekenstein's original guess. It was a stunning vindication for the young physicist who had dared to connect these seemingly disparate concepts, and it marked the birth of an entirely new field called black hole thermodynamics, a framework that would eventually point toward even more radical insights about the nature of reality itself. Hawking's 1974 discovery that black holes radiate should have been a triumphant moment, a beautiful resolution to a long-standing question about whether these cosmic monsters could have thermodynamic properties, but instead, it opened up what would become perhaps the deepest and most troubling crisis in all of modern theoretical physics. A paradox so profound that it threatened to tear down the entire framework of quantum mechanics itself. You see, Bekenstein had been vindicated in his claim that black holes possess entropy, and Hawking had provided the exact mathematical formula showing how that entropy related to the surface area of the event horizon. But in doing so, Hawking had also revealed something deeply disturbing about the nature of the radiation these objects emit. The problem wasn't just that black holes radiate, it was the specific character of that radiation. The fact that it appeared to be completely and utterly random, carrying absolutely no information about what had fallen into the black hole in the first place. This might not sound like a big deal at first glance, but it represented nothing less than a fundamental assault on one of the most sacred principles in all of physics, the law of information conservation, also known as unitarity. To understand why this was such a catastrophic problem, we need to step back and appreciate what information really means in the context of physics, and how it connects to everything we know about how the universe operates at the most fundamental level. Information in physics isn't some abstract philosophical concept. It's the concrete mathematical description of the state of a physical system, the complete list of properties that tells you everything there is to know about that system at a given moment in time. If you're tracking a baseball flying through the air, the information you need includes its position, its velocity, its spin, and with that information, plus the laws of physics, you can predict exactly where it will land. For more complex systems like a gas in a container, you'd need to know the position and momentum of every single molecule, which might number in the trillions upon trillions, far more than anyone could possibly keep track of by hand. This is where the concept of entropy comes in, providing a summary of how much information you'd need to completely specify the state of the system. How many different microscopic arrangements of particles could give rise to the same macroscopic properties you observe, like temperature and pressure. The key insight that emerged in the 20th century was that information and entropy are two sides of the same coin, intimately connected through mathematics, in a way that was first recognized by Claude Shannon in 1948. Shannon was working at Bell Labs during and after World War II, constantly scribbling equations on napkins during meals, thinking obsessively about communication and cryptography, how to encode messages efficiently and transmit them reliably through noisy channels. During the war, he had worked on classified projects and even met several times with Alan Turing, the brilliant mathematician who would help crack the German Enigma code. But Shannon's greatest contribution came in a groundbreaking 1948 paper, where he invented information theory and defined a mathematical measure of information content that he called entropy, using the same word that had been coined by Rudolf Clausius almost a century earlier in the context of thermodynamics. Shannon chose this term because his formula looked remarkably similar to the equation Ludwig Boltzmann had derived in the 1870s for thermodynamic entropy. Even though Shannon was approaching the problem from a completely different direction, thinking about communication and data compression, rather than heat engines and gas molecules, this similarity wasn't just a coincidence. It reflected a deep mathematical connection between the amount of information needed to describe a system and its thermodynamic entropy. When you measure the entropy of a gas, you're essentially quantifying how much information would be required to specify the exact microscopic state of all those particles, how many bits of data you'd need to completely describe their positions and velocities. Higher entropy means more possible microscopic arrangements, which means you need more information to pin down exactly which arrangement you're dealing with. And this connection between information and entropy leads directly to one of the most fundamental principles in quantum mechanics, the law that information can never be destroyed. In classical physics, this principle is related to time reversibility, the fact that the laws of mechanics work equally well, whether time flows forward or backward. So if you know the complete state of a system at one moment, you can, in principle, calculate both its future and its past with perfect accuracy. Quantum mechanics complicates this picture. By introducing fundamental uncertainty and probability, you can't know both the position and momentum of a particle with arbitrary precision. due to Heisenberg's uncertainty principle. But the evolution of quantum states is still governed by reversible equations that preserve information. The mathematical framework describing how quantum systems evolve over time, developed by physicists like Erwin Schrödinger and Werner Heisenberg in the 1920s, ensures that information is never lost, only transformed and redistributed. This principle, called unitarity, is absolutely fundamental to how quantum mechanics operates. It's baked into the very structure of the theory at the deepest level. If unitarity were violated, if information could actually be destroyed, then the entire predictive framework of quantum mechanics would collapse. You'd lose the ability to calculate probabilities for future quantum events, and the theory would cease to make sense. So when Hawking discovered that black holes emit radiation, physicists naturally wanted to know whether that radiation carried information about what had fallen into the black hole, whether it preserved the detailed quantum information about all those particles and fields that had crossed the event horizon. And this is where the disaster struck, because Hawking's calculations showed definitively that the radiation was purely thermal, meaning it had the same character as the radiation emitted by any hot object, completely random and carrying no information beyond the temperature itself. If you monitored all the particles and photons streaming away from an evaporating black hole, carefully measuring their properties and trying to reconstruct what had gone into making the black hole in the first place, you'd find it impossible. The radiation would look exactly the same, whether the black hole had formed from a collapsing star, from compressed information, from antimatter, or from any other source, as long as the final mass, charge, and spin were identical. This was a direct consequence of the no-hair theorem that Bekenstein had discovered, the fact that black holes only present three measurable properties to the outside world. Everything else gets hidden behind the event horizon, tucked away where it can never be observed or measured again. So imagine you create two completely different black holes, one by collapsing a massive star and another by compressing an enormous amount of pure radiation. But you adjust things so they end up with exactly the same mass, charge, and spin. According to classical general relativity, these two black holes would be absolutely indistinguishable, perfect twins, despite their completely different origins. Now let them sit there for billions of years, slowly evaporating through Hawking radiation, emitting particles one by one as they gradually shrink and lose mass. Since they have the same mass, and therefore the same temperature, they'll emit identical Hawking radiation, the same spectrum of particles, with the same energies, and the same random distribution. Eventually, after an incomprehensibly long time, both black holes will evaporate completely, disappearing in a final burst of radiation, and leaving behind nothing but a featureless cloud of particles and photons expanding into space. And here's the killer. If you analyze that final cloud of radiation, there would be absolutely no way to tell which original black hole it came from. No way to reconstruct whether it had been made from a star or from pure radiation. All the information about the initial state, all those intricate quantum details that went into building the black hole in the first place, would have simply vanished from the universe, destroyed utterly and completely, gone forever, with no possibility of recovery. This was the black hole information paradox in its starkest form, a direct frontal assault on the principle of unitarity, on the conservation of information that quantum mechanics absolutely required. Information goes in, nothing comes out, except random thermal radiation. And when the black hole finally evaporates completely, that information is just gone, erased from existence, in clear violation of the fundamental laws of quantum theory. Hawking himself was deeply troubled by this conclusion, but he felt the mathematics was airtight. He had used the best available tools, combining general relativity with quantum field theory in curved spacetime, and the answer seemed unavoidable. Black holes destroy information, period. This meant that either general relativity was wrong, or quantum mechanics was wrong, or both theories were incomplete in some fundamental way that became apparent only in these extreme situations where gravity and quantum effects both played crucial roles. The paradox created immediate camps among physicists, with some siding with general relativity and accepting that information might truly be lost, while others defended quantum mechanics to the death, insisting that information had to be preserved somehow, even if we didn't yet understand the mechanism. Stephen Hawking initially fell into the first camp, arguing that we might need to modify quantum mechanics to allow for information destruction, a radical suggestion that most quantum physicists found deeply unsatisfying. John Wheeler, Bekenstein's mentor and one of the great visionaries of 20th century physics, had coined the phrase "it from bit" to express his belief that information, not matter or energy, formed the deepest foundation of physical reality, that the universe was fundamentally made of information, and everything else was just different arrangements of those underlying bits. From Wheeler's perspective, the idea that black holes could destroy information was almost like suggesting they could destroy reality itself. And this is where the connection to entropy became crucial, because if entropy really was the same thing as information, as Shannon and Boltzmann's eerily similar formulas suggested, then measuring the entropy of a black hole should tell us how much information it contains. Bekenstein had already established that black hole entropy was proportional to the surface area of the event horizon, and Hawking's calculation had provided the exact proportionality constant, showing that you needed to measure areas in units of the Planck length squared to get the right answer. The Planck length is one of the most important fundamental constants in all of physics, derived by Max Planck himself in the early days of quantum theory by combining the speed of light, Newton's gravitational constant, and Planck's constant in just the right way. The result is an incredibly tiny distance, roughly 1.6 times 10 to the negative 35 meters, so small that it's hard to even comprehend. About 20 orders of magnitude smaller than a proton, representing the scale at which quantum effects of gravity become important. And our usual notions of smooth, continuous spacetime break down into what physicists call quantum foam. Using these Planck units, Bekenstein calculated in 1981 that there was a maximum amount of entropy, and therefore a maximum amount of information, that could be contained in any given region of space, and that maximum was achieved by black holes. The entropy inside a black hole, or equivalently the information content, was exactly proportional to the surface area of its event horizon measured in square Planck lengths, not to the volume inside. And here's the truly mind-blowing part. When you added one bit of information to a black hole by throwing in a particle, its event horizon grew by exactly 1 Planck area, 1 Planck length squared. Not approximately, not roughly, but exactly. This was a profound and disturbing result, because it suggested that information didn't care about volume the way we normally think it should. Instead, it cared about surface area, about two-dimensional boundaries rather than three-dimensional interiors. Everything we experience tells us we live in 3 spatial dimensions, that objects occupy volumes, and that bigger volumes should be able to store more information, like how a larger hard drive with more physical space can hold more data. But black holes were teaching us something radically different, that at the most fundamental level, information might be a two-dimensional phenomenon, living on surfaces rather than in volumes. And this wasn't just true for black holes. Bekenstein showed that any region of space, no matter what it contains, has an entropy limit proportional to its surface area. It's just that most ordinary objects fall far short of this maximum. Only black holes saturate the bound, packing in the absolute maximum possible information for their size. This discovery sent ripples through the theoretical physics community, because it suggested that our three-dimensional universe might somehow be less fundamental than we thought, that maybe the real action was happening on some two-dimensional boundary surface, with everything we experience as three-dimensional space being some kind of projection or hologram. But before physicists could fully explore these bizarre implications, They had to confront the more immediate crisis, the information paradox itself, the apparent fact that black holes could swallow information whole and then radiate it away as meaningless thermal noise, leaving no trace behind when they finally evaporated. Bekenstein and Hawking couldn't both be completely right. Either information had to be preserved somehow, perhaps encoded in subtle correlations within the Hawking radiation that the initial calculations had missed, or black holes had to retain some memory of what fell into them, some hair that violated the no-hair theorem and carried information on their surfaces. The resolution to this paradox would take decades of work and require insights from unexpected directions, but the key clue was already sitting there in Bekenstein's calculation, showing that information scales with surface area, pointing toward a radically new picture of reality that would eventually emerge from the study of string theory and lead to one of the most important ideas in modern physics, the holographic principle. The strange connection between black hole entropy and surface area that Bekenstein had discovered, and that Hawking had confirmed through his radiation calculations, was pointing towards something radically new, something that would require physicists to completely rethink their assumptions about how information works at the most fundamental level. But to understand where this revelation would lead, we need to step back from the cosmic monsters lurking in the depths of space and travel instead to a very different place and time, to Britain in the aftermath of World War II, where a brilliant young physicist named Denis Gabor was working on what seemed like a completely unrelated problem in optics and imaging. Gabor had been born in Budapest, Hungary, in 1900, and as a teenager, he had served in an artillery unit with the Austro-Hungarian army during World War I, fighting on the Italian front in that sprawling conflict that would reshape Europe and set the stage for even greater horrors to come. Between the wars, Gabor studied in Germany, becoming exceptionally skilled at working with electronics and electromagnetic radiation. But by the early 1930s, the rise of the Nazi regime put him in mortal danger. His Jewish heritage meant nothing to the Nazis despite his military service, and so in 1933 he fled, accepting an invitation to work in Britain, where he would spend the rest of his career. Despite this upheaval and the trauma of being forced to abandon his homeland, Gabor never lost his fascination with the behavior of light and electrons, and it was this obsession that would lead him to make one of the most remarkable discoveries in the history of physics, a technique he called holography. The word itself comes from the Greek words meaning whole writing or complete recording, and that name captures exactly what makes holography so revolutionary and so relevant to our story about black holes and information. When you take a normal photograph with a camera, whether it's an old film camera or a modern digital one, you're capturing a two-dimensional projection of a three-dimensional scene, and in that projection, you lose information, lots of it. Think about standing on a mountain trail, overlooking a spectacular valley. You can walk around, move your head, get different perspectives, see how the peaks in the distance shift relative to the foreground, observe the three-dimensional structure of the landscape from multiple angles. You have the freedom to explore the scene in its full three-dimensional glory. But the moment you pull out your phone and snap a picture, all that freedom vanishes. You're locked into one single perspective forever. The photograph is just a flat two-dimensional image, capturing light from one specific viewpoint. And if you print that photo and hang it on your wall, you can walk around the picture frame all you want, but you'll never see the other side of the mountain, never get a different angle on the valley, because all that information has been thrown away. Photography, by its very nature, is a lossy process. It takes three-dimensional reality and flattens it down to two dimensions, and in doing so, it necessarily destroys information about depth, about parallax, about all the details you could have seen if you just moved a little to the left or right. This seems like an inevitable limitation, just the price you pay for wanting to capture and preserve a visual scene. But Gabor discovered something absolutely extraordinary. He found a way around this limitation, a method for encoding complete three-dimensional information onto a two-dimensional surface without losing any data at all. The key was to use the wave nature of light in a clever way, by creating interference patterns between different light waves. When two waves overlap, they can add together constructively where their peaks align, creating brighter spots, or cancel out destructively where a peak meets a trough, creating darker regions, and the resulting pattern of light and dark fringes contains encoded information about the phase and amplitude of the original waves. Gabor realized that by carefully arranging the illumination of an object and recording the interference pattern created when light bouncing off that object mixed with a reference beam, he could capture not just the intensity of light at each point, which is all a regular photograph records, but also the phase information, the precise timing of the light wave oscillations. This phase information is what normal photography throws away, but it contains crucial data about the three-dimensional structure of the scene, and by preserving it in the interference pattern, Gabor found he could reconstruct the original light field in all its three-dimensional glory. When you illuminate a holographic recording properly, shining light through it at just the right angle, it recreates the same pattern of light waves that would have reached your eye if you were looking at the original object. And this means you can move your head and see different perspectives, walk around the hologram within limits, and observe it from different angles, just as you could with the real thing. The hologram isn't just a picture of an object, it's a complete recording of the light field, containing all the information needed to reproduce the full three-dimensional experience. Gabor made this discovery in 1947, but it didn't immediately capture the public imagination or even the attention of most scientists. The technology for creating and displaying holograms was primitive at the time, limited by the light sources available and the quality of recording materials, and it would take decades before holography moved beyond laboratory demonstrations. It wasn't until 1971 that Gabor was finally awarded the Nobel Prize for his invention, and even after that, most people encountered holography only as a science fiction novelty, like Princess Leia's message in the original Star Wars film, where she appears as a flickering three-dimensional projection, pleading for help, or perhaps as those cheap holographic stickers and trading cards that show different images when you tilt them. Though those aren't really holograms at all, just clever laminated printing that creates a pseudo three-dimensional effect. But while the general public saw holography as little more than an entertaining gimmick, the physics community quickly grasped its profound implications, because what Gabor had demonstrated was that under the right conditions, three-dimensional information could be perfectly encoded onto a two-dimensional surface, that you could take everything about a volumetric space and compress it down to a boundary without losing anything essential. This was exactly the opposite of what common sense would suggest. Normally, when you reduce dimensions, you lose information. Going from 3 dimensions to 2 dimensions means throwing away depth information, just like going from a 3-dimensional sculpture to a 2-dimensional photograph. But holography showed that this intuition was wrong. At least in certain special circumstances, it was possible to map all the information from a higher dimensional space onto a lower dimensional boundary while preserving everything, creating a perfect one-to-one correspondence between the 3-dimensional reality and its 2-dimensional representation. And this is where the connection to black holes becomes absolutely critical, because remember what Bekenstein had discovered about black hole entropy. He had found that the information content of a black hole, as measured by its entropy, was proportional to the surface area of the event horizon, not to the volume enclosed within it. In any normal object, entropy scales with volume. A bigger box of gas has more molecules, and therefore more entropy than a smaller box. But black holes violated this expectation. For them, it was the 2-dimensional surface area that mattered. When you added one bit of information to a black hole by tossing in a particle, the event horizon didn't expand in volume the way you'd expect. Instead, its surface area grew by exactly 1 Planck area, 1 Planck length squared. that incredibly tiny unit of area, about 10 to the negative 70 square meters, where quantum effects of gravity dominate. And it wasn't just that black holes had this weird property. Bekenstein had shown that any region of space, no matter what it contained, had a maximum entropy proportional to its surface area rather than its volume. It's just that ordinary matter and energy fall far short of this maximum. Only black holes actually saturate the bound, packing in the absolute most information possible for a given surface area. This was a deeply troubling result, because it suggested that our three-dimensional universe might not be quite as three-dimensional as it appeared, that maybe at the most fundamental level, information and entropy, and therefore perhaps reality itself, cared more about surfaces than volumes, more about two-dimensional boundaries than three-dimensional interiors. And when physicists familiar with Gabor's work on holography looked at Bekenstein's results, the parallel was impossible to miss. Both were telling us that three-dimensional information could somehow be encoded on two-dimensional surfaces. In 1993, two physicists, Gerard Hooft and Leonard Susskind, working independently but inspired by the same insights about black hole entropy, proposed what would become known as the holographic principle, the radical idea that our entire three-dimensional universe might be a kind of hologram, that all the information describing everything in a volume of space could be encoded on the boundary surface of that volume, just like how a holographic film encodes three-dimensional scenes on a two-dimensional plate. The principle states that the maximum amount of information contained in any region of space is proportional to the surface area of that region measured in Planck units, not to its volume, and that black holes achieve this maximum. They are the most information-dense objects possible. But the really mind-bending implication was that maybe three-dimensional space itself was somehow a projection or emergence from more fundamental two-dimensional physics happening on a distant boundary, that everything we experience as depth and volume and three-dimensional structure might be a kind of illusion, a holographic reconstruction from information stored elsewhere. Now, if this sounds completely crazy and impossible to believe, you're not alone. The holographic principle seemed to fly in the face of everything we know from daily experience. After all, we clearly live in three spatial dimensions. We can move forward and backward, left and right, up and down, and objects very obviously occupy volumes, not just surfaces. How could all of that be secretly two-dimensional? But the evidence from black holes was hard to ignore. The mathematics was clear and compelling. The entropy scaling with area rather than volume was a robust result that emerged from combining general relativity with thermodynamics and quantum mechanics, all theories that had been tested extensively and found to be remarkably accurate. And if black holes really did store information on their surfaces, if the event horizon really was a two-dimensional hologram encoding everything about the black hole's interior, then maybe this same principle applied more broadly to all of space-time. The holographic principle also offered a potential resolution to the black hole information paradox that had been tormenting physicists since Hawking's 1974 discovery. If black holes are genuinely holographic objects, then they don't really have an interior in the conventional sense, or at least not in the way we normally think about it. Instead, everything is encoded on the event horizon, on that two-dimensional boundary surface. Nothing truly falls into the black hole, because there is no in. There's only the surface, and everything that appears to cross the horizon actually gets smeared out and encoded across that surface in some complex way. When black holes emit Hawking radiation, they're radiating from this surface where all the information is stored, and if the information never really went inside in the first place, if it's always been sitting there on the boundary, then maybe the Hawking radiation can carry that information away after all, perhaps encoded in subtle quantum correlations that the original calculations had missed. This would mean that both Bekenstein and Hawking had been slightly wrong in their initial interpretations. Black holes do have entropy, and they do radiate, but they also have hair. They do retain information about what fell into them, just not stored in the interior volume. but rather encoded on the surface in patterns too subtle for the early calculations to detect. The information isn't lost, it's just been transformed and redistributed in an incredibly complex way across the event horizon. And when the black hole eventually evaporates completely, all that information gets released back into the universe through the Hawking radiation, preserving unitarity and saving quantum mechanics from disaster. Of course, this resolution was just a proposal, a promising idea that needed to be worked out in mathematical detail and tested against the rigorous requirements of quantum field theory and general relativity. But it gave physicists hope that the paradox might not be insurmountable after all, that there might be a way to reconcile black hole physics with the fundamental principles of quantum mechanics. And as researchers began exploring the holographic principle more deeply in the 1990s, they discovered it had implications far beyond just black holes. It suggested that the nature of space-time itself might be radically different from what anyone had imagined, that gravity and geometry might emerge from more fundamental quantum information processed on lower dimensional boundaries, and that our three-dimensional reality might be nothing more than a holographic projection, a shadow cast by information living elsewhere in a realm of fewer dimensions. The holographic principle that Hooft and Susskind proposed in the early 1990s was suggesting something so radical, so deeply counterintuitive, that even many physicists found it hard to swallow. But if it was true, if black holes really were holographic objects, rather than the three-dimensional monsters everyone had always assumed them to be, then it meant we had to completely reimagine what happens when matter falls toward an event horizon. And this reimagining would potentially solve the information paradox that had been plaguing theoretical physics for 2 decades. To understand what it means for a black hole to be holographic, we need to think carefully about what happens from 2 different perspectives, that of someone falling into the black hole and that of someone watching from a safe distance far away. For the infalling observer, the one who has decided to take the plunge past the point of no return, general relativity tells us something surprising. According to Einstein's equations, crossing the event horizon should be utterly unremarkable. There's no physical barrier there, no wall or membrane, just empty space that happens to be curved in a particular way by the black hole's enormous mass. An astronaut falling feet first toward a supermassive black hole would sail right through the horizon without even noticing the moment of passage, at least not initially, though they'd eventually be torn apart by tidal forces as they approach the singularity at the center where the curvature becomes infinite. But from the perspective of a distant observer watching through a telescope, things look completely different, and this difference is crucial to understanding the holographic nature of black holes. Due to the extreme gravitational time dilation near the event horizon, time appears to slow down dramatically for anything approaching that boundary. And this isn't just an optical illusion or a trick of measurement. It's a genuine feature of how space-time is warped by the black hole's mass. As an object gets closer and closer to the horizon, its clock appears to tick slower and slower from the viewpoint of the outside observer. And as it approaches the horizon asymptotically, getting infinitely close, but never quite reaching it in finite time as measured by the outside clock, something remarkable happens. The object appears to freeze, hovering just above the event horizon, its image getting dimmer and more red-shifted as the light escaping from it gets stretched to longer and longer wavelengths, but never quite disappearing entirely. From this external perspective, nothing ever actually crosses the horizon. Everything that falls toward a black hole gets stuck on the surface, smeared out across the 2-dimensional boundary, in a process that takes infinite time to complete. Now here's where the holographic principle becomes crucial, because if we take this outside perspective seriously, if we believe that from the viewpoint of any observer who remains outside the black hole, everything that falls toward it gets encoded on the event horizon rather than passing through, then maybe the event horizon isn't just a boundary marking where things disappear. Maybe it's actually the place where all the information about those things gets permanently stored. the holographic principle takes this observation and runs with it, proposing that the event horizon is literally a two-dimensional surface containing all the information about everything that has ever approached the black hole, encoded in some incredibly complex pattern of quantum fluctuations across that spherical boundary. In this picture, black holes don't have interiors in the conventional sense, or at least the interior isn't where the fundamental physics happens. Instead, the real action is all on the surface, on that two-dimensional holographic screen where information gets written and stored. When matter approaches the horizon, it doesn't tunnel through into some hidden three-dimensional volume behind the boundary. Instead, it gets spread out and encoded across the surface, like data being written to a hard drive, increasing the surface area by exactly 1 Planck area for every bit of information added. This is why the entropy scales with surface area rather than volume, because the information literally lives on the surface, not in the interior. The surface is where the degrees of freedom are, where the quantum states that describe the black hole's microstructure exist. Think of it like this. Imagine you're watching a very sophisticated hologram, a true three-dimensional holographic projection of the kind that Dennis Gabor invented, and you see what appears to be a complex three-dimensional object floating in space before you. You can walk around it, view it from different angles, and it looks completely real and three-dimensional, but you know that all the information creating that illusion is actually stored on a two-dimensional holographic plate somewhere, perhaps across the room or in another location entirely. The three-dimensional appearance is a projection, an emergent property that arises when light interacts with the two-dimensional information pattern in just the right way. Now imagine that, instead of a holographic plate, the information is stored on a spherical surface, the event horizon of a black hole, and instead of reconstructing a three-dimensional image for your eyes to see, it's reconstructing the appearance of a three-dimensional gravitational object, with mass and curvature, and all the properties we associate with a normal three-dimensional entity. From the outside, the black hole looks and acts like a solid three-dimensional object with volume. But fundamentally, at the deepest level, it's actually a two-dimensional surface with no interior. Or rather, the interior is a kind of illusion or emergent phenomenon that only exists relative to certain perspectives. This might sound like philosophical word games, but it has concrete mathematical consequences and potentially resolves the information paradox in an elegant way. Remember, the paradox arose because Hawking radiation appeared to be completely thermal and random, carrying no information about what fell into the black hole, which meant that when the black hole eventually evaporated completely, all the information about its contents would be lost forever, violating the fundamental principle of unitarity in quantum mechanics. But if the black hole is truly holographic, if nothing ever actually falls in, but instead gets encoded on the surface of the event horizon, then the information never really goes anywhere. It stays right there on the boundary where Hawking radiation is being emitted. The Hawking radiation doesn't have to somehow extract information from deep within the black hole's hidden interior, because there is no hidden interior. Everything is right there on the surface where the radiation originates. This means the radiation could in principle carry away all the information about what formed the black hole and what fell into it over its lifetime, not in any obvious or easy to decode way, but encoded in subtle quantum correlations between the particles being emitted. When you throw a book into a black hole, destroying all those pages filled with words and information, that information doesn't vanish into some inaccessible interior realm. Instead, it gets scrambled and spread out across the event horizon in an incredibly complex pattern, and as the black hole slowly evaporates through Hawking radiation, that scrambled information gets gradually released back into the universe, preserved in the quantum entanglement structure of the outgoing particles. It would be essentially impossible to reconstruct the original book from this radiation in practice. The information would be so thoroughly scrambled and encoded in such a complex way that you'd need computational power far beyond anything conceivable to decode it. But in principle, It's there. The information isn't destroyed, just transformed beyond recognition. This resolution requires modifying both Bekenstein's original picture and Hawking's initial calculation in subtle but important ways. Bekenstein had argued that black holes must have entropy, and that this entropy scaled with surface area, which was correct, but he had framed this in terms of information being hidden behind the horizon, stored somewhere inaccessible in the black hole's interior. The holographic picture says no. The information isn't hidden behind anything. It's right there on the surface, encoded in the quantum state of the horizon itself. And Hawking had calculated that black holes emit thermal radiation with no information content, which was also correct as a first approximation. But this calculation treated the event horizon as a smooth classical surface in a fixed space-time background, without accounting for the quantum fluctuations of the horizon itself, or the subtle correlations that could carry information. A more complete calculation that properly accounts for the quantum nature of gravity and the holographic structure of the event horizon would reveal that the radiation isn't perfectly thermal. After all, it contains tiny deviations from pure randomness, delicate correlations that encode information about the black hole's formation and history. Both physicists had been partially right and partially wrong. Black holes do have entropy that scales with area, and they do radiate, but they also have hair in the sense that they retain information about what fell in, just not stored in the way anyone had initially imagined, not as distinct features or irregularities in the event horizon that you could measure from outside, but rather in the complete quantum state of the horizon, in patterns that only become apparent when you consider the full quantum gravity description. This holographic picture of black holes also explains why they represent the maximum possible entropy density in the universe, why they saturate the Bekenstein bound that limits how much information can fit in a given region of space. If you try to pack more information into a region than the bound allows, more than 1 bit per Planck area of the bounding surface, the region will collapse into a black hole, which then saturates the bound exactly by spreading all that information across its event horizon. You can't exceed the limit because the very act of trying to do so creates a black hole that immediately redistributes the information onto its surface in a way that respects the bound. Black holes aren't exceptions to the rules of information storage. They're the ultimate expression of those rules. They show us the absolute maximum information density allowed by the laws of physics. But here's where things get really strange, because black holes aren't isolated curiosities. They're objects made entirely from the fabric of space-time itself, from pure geometry and gravity, with no other ingredients required. The fact that they're holographic, that their fundamental description involves information living on two-dimensional surfaces rather than in three-dimensional volumes, suggests that maybe this property isn't unique to black holes. Maybe it's a fundamental feature of space-time itself. If the most extreme gravitational objects in the universe, the places where gravity is strongest and most dominant, turn out to be secretly two-dimensional rather than three-dimensional, then perhaps space and time themselves have this character. Perhaps the three-dimensional universe we experience is itself a holographic projection from information encoded on some distant two-dimensional boundary. This is exactly what the holographic principle, in its most general form, proposes, that the description of physics in any region of space can be encoded on the boundary of that region, with 1 degree of freedom per Planck area, and that the three-dimensional appearance of that region is somehow emergent or derived from the more fundamental two-dimensional physics on the boundary. It's as if the entire universe is like a black hole in this respect, not in the sense of having an event horizon or singularity, but in the sense that its fundamental description lives on a surface rather than throughout its volume. That depth and interior space are illusions or emergent properties rather than fundamental aspects of reality. And this isn't just wild speculation. It's a serious research program that has produced concrete results and deeper understanding of how gravity and quantum mechanics might fit together. But to see how this works in detail, to understand how you can actually do calculations with holographic theories and make predictions, we need to leave behind black holes for a moment and venture into the strange world of string theory, where in 1997, a physicist named Juan Maldacena would discover the most precise and powerful example of holography in action, a mathematical correspondence that would revolutionize theoretical physics and provide the strongest evidence yet that we really might be living in a hologram. By the mid-1990s, theoretical physics was in a strange place, caught between extraordinary promise and frustrating obstacles that seemed impossible to overcome. And nowhere was this tension more apparent than in string theory, the ambitious framework that proposed to unify all the forces of nature by replacing point-like particles with tiny vibrating strings of energy. String theory had emerged in the 1970s and 80s as a potential candidate for the long-sought theory of everything, a single mathematical framework that could reconcile quantum mechanics with general relativity and explain all the particles and forces in the universe as different vibrational patterns of these fundamental strings. The mathematics was elegant and beautiful, and the theory made several remarkable predictions, including the necessary existence of gravity, which emerged naturally from the vibrations of closed strings, something no other quantum theory had managed to achieve. But string theory came with a peculiar requirement that many found disturbing. It only worked mathematically if the universe had not 3 spatial dimensions, but 9, or in some versions 10, or even 11 when you included time. These extra dimensions had to exist for the equations to make sense, for the quantum mechanics of the strings to remain consistent and avoid mathematical contradictions and anomalies. Of course, we don't see these extra dimensions in our everyday experience. We only perceive 3 spatial dimensions plus time, so string theorists proposed that the extra 6 or 7 dimensions must be curled up or compactified into incredibly tiny shapes, so small that we can't detect them directly, existing at every point in space, but wrapped up at scales far below what any microscope or particle accelerator could probe. This led to an explosion of possible string theory models, because there are countless different ways you could curl up these extra dimensions, different geometric shapes and topologies, and each choice would lead to different physics in the remaining large dimensions, different particles, different force strengths, different physical laws. The theory that was supposed to be unique and explain everything had turned into a vast landscape of possibilities, with an estimated 10 to the 500th power, different vacuum solutions, different versions of string theory, corresponding to different ways the extra dimensions could be arranged. And beyond this embarrassment of riches, string theory faced a more immediate practical problem. The equations were brutally difficult to solve, in most cases, essentially impossible to work with using existing mathematical techniques. String theory, in its full glory, incorporating gravity and quantum mechanics in higher dimensional curved spacetimes, was so mathematically complex that physicists couldn't make detailed predictions or test whether the theory actually described our universe. They were stuck with approximation methods that only worked in certain limited regimes, unable to probe the theory's behavior in the strongly interacting situations where quantum gravity effects became important, exactly the situations they most wanted to understand, like the interior of black holes or the moment of the Big Bang. This was the frustrating landscape that confronted Juan Maldacena when he arrived at Princeton University as a young postdoctoral researcher in the mid-1990s, having just completed his PhD at the Institute for Advanced Study, where he had been working on various aspects of string theory and black hole physics. Maldacena was born in Buenos Aires, Argentina in 1968, and had shown exceptional mathematical talent from an early age, eventually studying physics at the Instituto Balsero in Barillo before moving to the United States for graduate work. He was brilliant and ambitious, known among his colleagues for his remarkable physical intuition and his ability to see connections between seemingly disparate areas of theoretical physics. And he was deeply fascinated by the holographic principle that Hooft and Susskind had proposed. The idea that black holes and perhaps the entire universe might be holographic in nature, with information living on lower dimensional boundaries rather than throughout higher dimensional volumes. But the holographic principle at that point was still just an idea, a suggestive but vague notion, without a concrete mathematical realization that physicists could actually calculate with and test. What was needed was a specific example, a toy model, where you could explicitly see holography at work, where you could point to a particular lower dimensional theory and show exactly how it encoded information about a higher dimensional space, and where you could perform calculations on both sides and verify that they gave the same answers. This is what Maldacena set out to find, and in late 1997, at the almost absurdly young age of 29, he published a paper that would become the most cited article in the history of high-energy physics, a 12-page manuscript that revolutionized our understanding of quantum gravity and provided the first concrete calculable example of the holographic principle in action. What Maldacena discovered, in what would come to be known as the AD/CFT correspondence, was a precise mathematical duality, an exact equivalence between two completely different theories, living in different numbers of dimensions. On one side of the correspondence was string theory in a 5-dimensional space with a particular geometry called anti-de Sitter space, or ADS for short, named after the Dutch astronomer Willem de Sitter, who had studied various solutions to Einstein's equations of general relativity. Anti-de Sitter space is a curved spacetime with constant negative curvature, kind of like the 3-dimensional version of a saddle shape, extending in all directions, and it has some peculiar properties that make it mathematically tractable, including the fact that its boundary at spatial infinity has one fewer dimension than the interior, so a 5-dimensional AD space has a 4-dimensional boundary. On the other side of Maldacena's correspondence was a completely different type of theory called a conformal field theory, or CFT, a quantum field theory with special symmetry properties living on that 4-dimensional boundary of the AD space, a theory with no gravity at all, just quantum particles and fields interacting according to the rules of quantum mechanics. And Maldacena's stunning claim was that these two theories, despite appearing completely different and living in different numbers of dimensions, were actually exactly equivalent. They were two different descriptions of the same underlying physics, related by a kind of mathematical dictionary that allowed you to translate questions in one theory into equivalent questions in the other. If you wanted to calculate some physical quantity in the 5-dimensional gravitational string theory, like the mass of a black hole or the behavior of gravitational waves, you could instead perform an equivalent calculation in the 4-dimensional non-gravitational quantum field theory and get exactly the same answer. The interior physics with gravity was holographically encoded in the boundary physics without gravity. This was holography made completely concrete and precise for the first time. Not just a vague principle, but an explicit mathematical correspondence where you could point to specific objects and interactions in both theories and show exactly how they matched up. A black hole in the 5-dimensional AD space, for example, would correspond to a hot thermal state of the quantum field theory on the 4-dimensional boundary, a collection of particles in thermal equilibrium at some temperature. Gravitational waves rippling through the interior space would correspond to particular patterns of quantum excitations propagating across the boundary. Everything happening in the higher dimensional volume could be described equivalently by physics on the lower dimensional surface. The implications were staggering, and the physics community recognized it immediately. Within months of Maldacena's paper appearing, hundreds of physicists around the world were working on extensions and applications of the AD-CFT correspondence. And within a few years it had accumulated thousands of citations, becoming one of the foundational pillars of modern theoretical physics. Leonard Susskind, one of the founders of string theory and the holographic principle, would later call Maldacena perhaps the greatest physicist of his generation, certainly the greatest theoretical physicist of his generation. The correspondence solved several problems simultaneously. First, it provided a concrete realization of the holographic principle, showing explicitly how information in a gravitational theory could be encoded on a lower dimensional boundary. Second, it gave physicists a powerful new tool for doing calculations in situations where traditional methods failed. If you had a hard problem in quantum gravity that you couldn't solve, you could try translating it into the equivalent problem in the boundary quantum field theory, which often had better mathematical techniques available, allowing calculations that were impossible in the gravitational description to become tractable in the holographic description. Third, and perhaps most importantly, it suggested that quantum gravity might not be a conventional quantum field theory at all, but rather might emerge from the collective behavior of more fundamental quantum degrees of freedom living on lower dimensional surfaces. Gravity and space-time themselves might be holographic phenomena, emergent properties that arise when you have the right kind of quantum entanglement structure in a lower dimensional system. The AD-CFT correspondence also provided new insights into the black hole information paradox that had motivated much of this research in the first place, because in the boundary quantum field theory description, which had no gravity at all, the evolution was manifestly unitary. Information was obviously conserved because it was just ordinary quantum mechanics with no black holes to swallow things up. And since the boundary theory was exactly equivalent to the gravitational theory in the interior, this meant that the gravitational theory must also conserve information. Even when black holes form and evaporate, the information couldn't really be destroyed. It had to be encoded somehow in the Hawking radiation, or in subtle correlations that the early calculations had missed. The correspondence didn't immediately tell you exactly how this information encoding worked in detailed mechanical terms, but it proved that it must work somehow, that unitarity must be preserved, because the holographic dual theory so obviously preserved it. Over the following decades, physicists would explore thousands of different aspects of the AD-CFT correspondence, using it to study black hole thermodynamics, quantum entanglement, the emergence of space-time from quantum information, and even applications to completely different areas of physics, like condensed matter systems and the behavior of strongly interacting plasmas created in particle accelerators. The mathematics involved became increasingly sophisticated, developing powerful new tools like tensor networks and quantum error-correcting codes to understand how bulk geometry in the interior space emerges from entanglement patterns in the boundary theory, how collections of quantum degrees of freedom, arranged in just the right way, with just the right correlations, could give rise to the appearance of an additional spatial dimension, complete with smooth geometry and gravitational dynamics. Maldacena himself continued to make major contributions, showing how various physical observables in gauge theories could be computed using string theory techniques, proposing that eternal black holes could be understood as entangled states connecting two copies of the boundary theory, and developing new tools for understanding quantum gravity through holographic duality. His original paper from 1997 has now been cited over 20,000 times, an almost unprecedented number in physics literature, and the AD-CFT correspondence has become a standard tool taught to graduate students in theoretical physics programs around the world. But despite all this success, it's crucial to understand what the AD-CFT correspondence does and doesn't tell us about the actual universe we inhabit. The correspondence is a duality between string theory in anti-de Sitter space and quantum field theory on its boundary. But our universe doesn't have anti-de Sitter geometry. It has a different kind of curvature, more like de Sitter space with positive curvature due to dark energy causing accelerated expansion. So the AD-CFT correspondence isn't a direct description of our cosmos. It's more like a toy model, a simplified scenario where we can see holography working explicitly and develop the mathematical tools and physical intuition needed to understand how quantum gravity operates. The hope is that lessons learned from studying this toy model can eventually be extended and generalized to more realistic cosmological settings that better match our universe, but that work is still ongoing and faces significant technical challenges. Nevertheless, what Maldacena achieved was revolutionary. He showed that the holographic principle wasn't just philosophical speculation, but could be made mathematically precise and concrete. He provided the first explicit example of how a lower dimensional quantum theory could perfectly encode a higher dimensional gravitational spacetime, and he opened up an entirely new approach to quantum gravity that has dominated theoretical physics research for more than 2 decades, suggesting that space and time and gravity itself might not be fundamental ingredients of reality, but rather emergent holographic projections from deeper quantum structures living in fewer dimensions. Maldacena's discovery of the AD-CFT correspondence had proven that holography wasn't just a beautiful idea, but a concrete mathematical reality, at least in carefully constructed toy universes with anti-de Sitter geometry. But this left an obvious and deeply unsettling question hanging in the air. If holography works in those artificial settings, if information about a higher dimensional gravitational universe can be perfectly encoded on a lower dimensional boundary, then what about our universe, the real cosmos we actually inhabit with its stars and galaxies, and the mysterious dark energy causing space to expand ever faster? Could our 3-dimensional reality also be holographic? Could everything we experience as depth and volume and spatial extension actually be a projection from information living on some distant 2-dimensional surface? And if so, where is that surface, and what does it mean for the nature of reality itself? To understand what physicists now suspect about the holographic character of our universe, we need to step back and appreciate just how strange the full picture of string theory and its modern extensions really is. Because the story doesn't end with tiny vibrating strings in 10 or 11 dimensions. It extends to include much larger extended objects called branes, short for membranes, that can have various dimensionalities, and that might, in some scenarios, constitute the very fabric on which our entire observable universe exists. The realization that string theory required these extended objects came gradually through the 1990s as physicists explored different aspects of the theory and discovered surprising connections between what had initially seemed like 5 completely separate versions of string theory, each with its own rules and properties. There was type I string theory, with both open and closed strings, type 2A, and type 2B theories that included only closed strings, but with different properties, and 2 versions of heterotic string theory, combining different mathematical structures. Having 5 different candidates for a theory of everything was embarrassing. It suggested that string theory wasn't really unique or fundamental, just a collection of different models. But then physicists began discovering dualities, mathematical transformations, showing that these apparently different theories were actually just different descriptions of the same underlying reality, like looking at the same object from different angles. Some of these dualities involve changing the strength of interactions, taking a theory where strings interacted strongly and transforming it into a different theory where strings interacted weakly, which meant calculations that were impossible in one description became easy in the dual description. Other dualities involve changing the size of compactified dimensions, showing that a theory with one set of curled-up dimensions could be mathematically equivalent to a completely different-looking theory with different dimensional structure. And as physicists mapped out these connections, they realized that all 5 string theories were actually parts of a larger unified framework that Edward Witten, one of the giants of modern theoretical physics, dubbed M-theory in 1995. The M could stand for membrane, or matrix, or mystery, or mother of all theories. Witten never specified and seemed to enjoy the ambiguity. M-theory lives not in 10 dimensions, like the various string theories, but in 11 dimensions, 10 spatial dimensions, plus time. And in this higher dimensional setting, the objects that had seemed fundamental in string theory, those one-dimensional vibrating strings, turned out to be just one type of entity in a much richer landscape of possibilities. Min theory includes not just strings, but also higher dimensional objects called brains, named after membranes, but extended to various dimensionalities. You could have 0 brains that are point-like particles, 1 brains that are strings, 2 brains that are actual membranes, like sheets of fabric extending through space, 3 brains that are 3-dimensional volumes, and so on up to 9 brains, filling 9 spatial dimensions in the theory. These brains aren't just mathematical curiosities, they're dynamical objects that can move through space, vibrate, interact with each other, and with strings. And most importantly for our story, they can carry information and support physical fields, living on their surfaces or within their volumes. And here's where things get truly mind-bending, because some physicists have proposed that our entire observable universe, everything we can see and measure and experience, might actually be a 3-brain, a 3-dimensional membrane, floating in the higher dimensional space of M-theory, or string theory. In this picture, all the matter and energy we know about, all the particles that make up atoms and molecules and stars and galaxies, would be confined to this 3-brain, stuck to its surface like insects crawling on a sheet of paper, unable to move in the extra dimensions that extend perpendicular to the brain. Only gravity, which in string theory and M-theory arises from the vibrations of closed strings that aren't attached to brains, would be able to propagate through the full higher dimensional space, which might explain why gravity seems so much weaker than the other forces. It's diluted by spreading out through extra dimensions, while electromagnetism and the nuclear forces are concentrated on our 3-brain. This scenario, called the brain-world hypothesis, was developed in the late 1990s by physicists like Lisa Randall and Raman Sundram, who showed that you could construct consistent models where lower dimensional brains existed in higher dimensional spaces, and where the physics on the brain could look very much like what we observe in our universe. In some of these models, the extra dimensions don't even need to be tiny and compactified. They could be large, or even infinite, as long as the matter and energy we know about is confined to the brain. The brain world idea immediately raises the question of whether other brains might exist parallel to ours, other 3-dimensional universes floating in the higher dimensional space, like parallel sheets of paper stacked next to each other, close enough to affect each other through gravitational interactions, but otherwise isolated, unable to exchange light or matter. These parallel brains could be mere micrometers away from us in the extra dimensions, close enough that their gravity warps space-time on our brain. But we'd never see them directly, because photons can't jump between brains. They're confined to the surfaces they originate from. Some cosmologists have even proposed that the Big Bang itself might have been the result of 2 brains colliding, releasing enormous energy that got converted into the hot, dense state from which our universe expanded, and that the universe might undergo cycles of expansion, collision, and rebirth as brains repeatedly crash together over cosmic timescales. But for our purposes, the most important aspect of the brain world picture is how it connects to holography. Because if our 3-dimensional universe is actually a 3-brain embedded in higher dimensional space, then the holographic principle suggests that all the information about our universe, everything that has ever happened and ever will happen on this brain, could in principle be encoded on the 2-dimensional boundary of that brain, on a surface surrounding the volume we inhabit. This is the ultimate realization of the insight that started with black holes and Bekenstein's calculation, showing that entropy scaled with surface area extended now not just to isolated objects, but to the entire cosmos. Our universe, in this picture, would be like a gigantic hologram with the true fundamental description living on a distant boundary surface, perhaps at the edge of space, infinitely far away, and everything we experience in the interior, all the depth and structure and three-dimensional character of reality would be a projection or emergence from that more fundamental two-dimensional physics. When you look at a star 1,000 light-years away, you think you're seeing a three-dimensional object embedded in three-dimensional space, but the holographic principle suggests that the real physics, the actual information processing that gives rise to that appearance, is happening on a two-dimensional surface, with the three-dimensional picture being a derived or emergent phenomenon, not the fundamental reality. This isn't saying that three-dimensional space is an illusion in the sense of being fake or unreal. It's more subtle than that. The three dimensions we experience are real and physical, but they might not be fundamental. They might emerge from more basic two-dimensional physics, the way that temperature emerges from molecular motion, or the way that waves on the ocean's surface emerge from the collective motion of water molecules. The holographic description and the three-dimensional description are two equivalent ways of talking about the same physical reality, related by a mathematical dictionary, like the one Maldacena discovered in the AD-CFT correspondence. And depending on what question you're asking, or what calculation you want to do, one description might be more useful than the other. For some problems, thinking in terms of particles moving through three-dimensional space is easier, while for others, translating to the holographic description on the boundary might make the calculation simpler or reveal connections that weren't obvious in the three-dimensional picture. Now you might be wondering, if this is true, if we really do live on a holographic membrane with our physics encoded on some distant two-dimensional boundary, why don't we notice it? Why does everything seem so obviously three-dimensional if that's not the fundamental reality? The answer is that the holographic encoding is incredibly subtle and only becomes apparent when you look at very specific aspects of physics, particularly those involving gravity and quantum mechanics together. For everyday phenomena, for the motion of projectiles, or the orbits of planets, or the behavior of atoms and molecules, the three-dimensional description works perfectly, and the holographic nature of space-time makes absolutely no difference to any calculation you'd want to do. It's only when you probe the most extreme conditions, like the physics of black holes, or the early universe, or the deepest structure of space-time itself at the Planck scale, that the holographic character becomes important and starts affecting predictions. And even then, we don't have direct experimental evidence for holography in our actual universe. What we have instead is strong theoretical arguments based on black hole thermodynamics and string theory calculations, suggesting that holography must be true, combined with the explicit example of AD-CFT, showing that holography definitely works in at least some universes, even if not precisely in ours. The challenge is that our universe doesn't have anti-de Sitter geometry. It has more like de Sitter geometry, with positive curvature due to dark energy, and constructing a precise holographic description for de Sitter space has proven much more difficult than for anti-de Sitter space. It remains an active area of research where physicists are still working out the details. Some researchers have proposed that the holographic boundary for our universe might be related to the cosmic event horizon, the boundary beyond which objects are receding from us faster than light due to cosmic expansion, meaning we can never receive signals from them, no matter how long we wait. This horizon acts like the boundary of our observable universe, and perhaps information about everything within that horizon is encoded on its surface in a holographic way, though the mathematics of making this precise is still being developed. What we can say with confidence is that the journey from Bekenstein's initial insight about black hole entropy scaling with area, through Hawking's discovery of black hole radiation, through Hooft and Suskind's articulation of the holographic principle, through Maldacena's proof that holography works in AD space, and now to the modern brain world scenarios, suggesting our entire universe might be a holographic projection from a two-dimensional membrane. represents one of the most profound shifts in our understanding of physical reality, since Einstein's relativity and quantum mechanics revolutionized physics in the early 20th century. We're learning that dimensions themselves might not be what we thought, that what seems most obvious and fundamental about our experience of space might actually be emergent and holographic, that the universe might be weirder and more subtle than our three-dimensional intuitions suggest, and that the Victorian dreamers who imagined higher dimensions and H.P. Lovecraft, who wrote about characters exploring impossible geometries, might have been pointing, in their own confused ways, toward genuine truths about the structure of reality. So where does this leave us, standing here in the mid-2020s, looking back at nearly 50 years of research into black hole thermodynamics and holography, trying to make sense of what physicists have discovered about the possible holographic nature of our universe? The honest answer is that we find ourselves in a strange liminal space, poised between revolutionary insight and profound uncertainty, between mathematical beauty that seems too elegant to be wrong and experimental silence that refuses to confirm what the equations seem to be telling us. The holographic principle, for all its theoretical appeal and mathematical sophistication, remains exactly that: a principle, a conjecture, a beautiful idea supported by compelling arguments and indirect evidence, but not yet elevated to the status of proven fact through direct experimental verification. And this uncertain status isn't just a temporary inconvenience that will be resolved next year or the year after. It reflects deep challenges in how we test theories about the fundamental nature of space-time itself, about physics at energy scales and distance scales so extreme that our current technology can't come anywhere close to probing them directly. The Large Hadron Collider, that magnificent 17-mile ring of superconducting magnets beneath the French-Swiss border, that represents the pinnacle of human experimental capability, can smash protons together at energies reaching 14 trillion electron volts, creating conditions that haven't existed in the universe since microseconds after the Big Bang. But even this incredible machine falls laughably short of the energies needed to directly test quantum gravity, which only becomes important at the Planck energy scale of about 10 to the 19th billion electron volts, roughly a quadrillion times beyond what the LHC can achieve. To build an accelerator that could reach Planck energies would require a machine larger than the solar system, a completely impractical fantasy that tells us we need to find cleverer, more indirect ways to test these ideas. And that's what makes the current situation so frustrating and so exciting simultaneously. Physicists have constructed this elaborate edifice of ideas about holography and string theory and extra dimensions and brains, all built on solid mathematical foundations and connected through intricate webs of logical reasoning. Yet they can't quite figure out how to definitively test whether any of it actually describes our universe. The AD-SCFT correspondence that Maldacena discovered, which remains the crown jewel of holographic physics, with over 20,000 citations, making it the most referenced paper in the history of high-energy theory, describes a universe with anti-de Sitter geometry, a space with constant negative curvature that curves inward on itself. But our actual universe doesn't look like that at all. We live in a space that's essentially flat on large scales with a tiny positive cosmological constant, causing accelerated expansion, making our cosmos more like de Sitter space than anti-de Sitter space. This might seem like a technical detail, but it's actually a huge problem because the mathematical techniques that work so beautifully in anti-de Sitter space break down or become much more complicated when you try to apply them to de Sitter space, or to flat space like our own. Physicists have been struggling for more than 2 decades to find a de Sitter version of the AD-CFT correspondence, a holographic description that would apply to universes more like ours. And while there's been progress and many clever proposals, Nothing has achieved the same level of precision and computational power as the original anti-de Sitter example. Some researchers think this difficulty might be telling us something profound, that perhaps de Sitter space is fundamentally unstable or unnatural from the perspective of quantum gravity, that maybe the universe shouldn't have a positive cosmological constant at all, but obviously it does. We measure it through observations of distant supernovae and the cosmic microwave background, so either our understanding is incomplete, or there's some subtle feature of how quantum gravity works in expanding universes that we haven't grasped yet. And then there's the question of string theory itself, the broader framework within which holography naturally emerges, in which has faced increasing skepticism from some corners of the physics community. After decades of work without producing clear, testable predictions that could be verified or falsified experimentally, string theory was supposed to predict the masses of particles, the strengths of forces, the value of the cosmological constant, all the parameters of the standard model that currently have to be measured experimentally should in principle emerge as consequences of the theory. But instead, string theory turned out to have that vast landscape of 10 to the 500th power possible solutions, making it seem more like an unfalsifiable framework that could accommodate almost any observation rather than a genuine predictive theory. The Large Hadron Collider was supposed to find evidence of supersymmetry, that beautiful mathematical symmetry relating bosons and fermions that emerges naturally in string theory and helps solve several problems in particle physics. But run after run, collision after collision, the LHC found nothing beyond the standard model particles we already knew about. No supersymmetric partners, no extra dimensions, no sign that nature used any of the elegant mathematical structures that string theorists had been so confident must be there. This doesn't prove string theory is wrong. Absence of evidence isn't evidence of absence. And maybe supersymmetry exists, but at higher energy scales than the LHC can reach. But it has definitely dampened enthusiasm and made some physicists wonder whether the entire string theory program might be a wrong turn, a beautiful mathematical edifice that doesn't actually describe physical reality. Yet despite all these doubts and uncertainties, the holographic principle keeps coming back, keeps reappearing in different contexts, keeps providing insights that seem too deep and too consistent to be mere coincidence. Beyond the original black hole calculations, physicists have found holographic dualities in condensed matter systems, in the behavior of strongly interacting quarks and gluons, in quantum information theory and entanglement structure, in contexts far removed from string theory and quantum gravity, suggesting that holography might be a more general principle about how information works in physical theories, not just a peculiar feature of gravitational systems. Researchers at Utah State University and other institutions have been developing new mathematical tools to test the holographic principle more rigorously, looking for precise predictions that might eventually be confronted with observation, while other groups have been exploring whether the strange noise patterns detected by gravitational wave detectors like GEO 600 might be signs that space-time is grainy or pixelated at tiny scales, exactly what you'd expect if space was a holographic projection rather than a smooth continuum. The cosmic microwave background, that faint afterglow of the Big Bang, still visible as microwave radiation coming from all directions in the sky, might contain subtle imprints of holographic structure if researchers can figure out what signatures to look for. And there are deeper philosophical questions lurking beneath all the mathematics and experimental challenges. Questions about what it would mean for us, for consciousness, for the nature of existence itself, if the holographic principle turned out to be true. If space really is emergent rather than fundamental, if the three-dimensional world we experience is a projection from information encoded on a distant two-dimensional boundary, then what does that say about causation, about free will, about the relationship between mind and matter? Some researchers have drawn parallels to simulation theory, The idea that we might be living in an elaborate computer simulation run by some advanced civilization, though most physicists are quick to point out that the holographic principle doesn't require any artificial creator. It's not saying we're in a simulation in that sense, just that the fundamental description of reality might work very differently than our everyday experience suggests. Information would be more fundamental than matter or energy. The patterns encoded on the holographic boundary would be what's really real, with particles and forces and space itself being emergent phenomena that arise from those more basic information structures. This connects to ideas John Wheeler explored late in his career under the banner It from Bit, the notion that existence itself, the it of physical reality, ultimately derives from information, from binary yes or no questions, from bits of quantum information entangled in precisely the right ways. And as we push further into the 21st century, as quantum computers become more sophisticated and allow physicists to simulate increasingly complex quantum systems, as gravitational wave detectors grow more sensitive and reveal more about the fabric of space-time, as new telescopes peer deeper into the early universe and probe the cosmic microwave background with ever greater precision, we might finally start to get the experimental data needed to test whether holography is more than just elegant mathematics, or we might discover that we've been on the wrong track entirely, that the real theory of quantum gravity looks nothing like string theory or holography, that nature has tricks up her sleeve that we haven't even begun to imagine. What remains certain is that the journey itself has been remarkable, from Bekenstein's bold proposal that black holes have entropy proportional to area, through Hawking's discovery that black holes radiate, through the information paradox that seemed to threaten quantum mechanics itself, through Gaber's invention of holography and Shannon's insights about information, through Tooft and Susskind articulating the holographic principle, through Maldaceno's stunning discovery of AD-CFT correspondence, all the way to our current understanding that space-time itself might be holographic, woven from quantum information living on lower dimensional surfaces. We stand now where Victorian scientists once stood, contemplating the fourth dimension, or where H.P. Lovecraft's character Walter Gilman stood at the threshold of impossible geometries, peering into realms our intuitions struggle to comprehend, except this time we have mathematics as our guide, equations that point the way even when our imaginations fail. The question of whether we live in a hologram, whether our three-dimensional reality is ultimately a projection from some two-dimensional membrane encoding all the information about our existence, remains open, tantalizingly close to being answered, yet still maddeningly out of reach. Perhaps within our lifetimes, we'll know for certain, or perhaps it will take centuries more of theoretical and experimental work before humanity finally understands the deepest nature of space and time and reality itself. But that uncertainty, that sense of standing at the edge of knowledge, peering into mystery, is exactly what makes physics exciting, what drives researchers to spend decades working on problems that might not be solved in their lifetimes, what transforms our understanding of existence from obvious common sense into something strange and beautiful, and far more subtle than anyone could have guessed. The universe may or may not be a hologram, but the fact that we can even ask the question coherently, that we have mathematical frameworks sophisticated enough to make the idea precise and testable, represents a triumph of human curiosity and ingenuity that would have been unimaginable to our ancestors. And whatever the final answer turns out to be, the journey of discovery itself reveals that reality is far stranger and more wonderful than we ever dared to imagine.